Right, so this is part 2 of the extended forces in motion topic. In this part we're going to look at the next type of motion graphs called speed time graphs. Now these in fact are even more useful than distance time graphs. There are two main things you can get extra from these graphs: acceleration as equal to the gradient, and distance as equal to the area under the speed time graph. Now you can't quite see, but that word there is acceleration, and that's distance. So those are the two things you can get apart from speed from the graph. Now the example below, you can see quite straight away that this object, whatever it is moving at a constant speed v of 8 meters per second for a time of 6 seconds. So straight away we can see information about speed, as you'd expect. Now looking at the slope, it's a straight line, flat line I should say, so there is no slope. Therefore we can say with confidence that the acceleration is 0. That makes sense because we have a constant speed of 8. The area under the graph, this shaded area here, is equal to the distance. So we can calculate that distance as an area, simply multiplying 8 times 6 for the area of that rectangle, and we get, of course, 48 meters. Right, so here are two more examples. For each one we can calculate the slope to find the acceleration and the area under the graph to find the distance. So for this first example here, looking at that slope to find the acceleration, we have the rise over run, which here's the rise from 0 up to 8. So that's our change in speed v, and that's over time, of course, which is the run. So that's 8 for our rise divided by 5 for the change of time or the run, and of course that gives us a bit over 1, more precisely 1.6 meters per second squared for the unit. The distance is found by the area under the graph. In this case we have a triangle, so half base times height will give us the area, half times 5 times 8. So what's that? That's going to be 20 meters. So the next example, here's our rise from 8 to 20. So we are going to put 12 for our rise, and the run 5 seconds. So acceleration in this case is 12 divided by 5 gives us 2.4 meters per second squared. The distance, we need to add two areas here. This rectangle area at the bottom and this triangle area at the top, because all of that is under the line of the graph down to the x-axis, or the time axis in this case. So it's that entire area there that we need to calculate. So we find the rectangle straightforward. It's 8 times 5, which is 40, plus this triangle here, half base times height will be half times 5 times 12, which should give you 30 meters. So total distance 70. Just check it yourself and see that you agree. Okay, here are two more examples. The first one, the acceleration can be found as the change of speed over time. The change of speed is from 12 down this time to 0. So we signify that with a negative sign, minus 12. And the time it took is 4. So there's our acceleration calculated. It's a negative acceleration because the speed is slowing down, of course. -3 meters per second squared. Our distance, of course, travelled during this slowing down is that area there, is the area of the triangle. So distance equals half base times height, half times 4 times 12, which would be 24 meters. Check it for yourself, make sure you agree. Second example here, acceleration in this case is going to be from 15 down to 9, that's our change of speed, -6 divided by the time it took, which was 4 seconds. So we have a -1.5 meters per second squared for acceleration. For the distance, it's the area under the graph. Again, it's this triangle here plus this rectangle there. So we need to add that. So 9 times 4 is 36 for the rectangle, that's straightforward, and the triangle 6 times 4 times a half base times height, so it'll be 12, so we get 48 meters for that. Okay, how to measure speed with a data logger. Well, we're going to do this in class. So we're going to investigate the terminal velocity of paper cups, and we're going to use a motion sensor joined to a data logger in order to gather data. So what you need to do though is think about how to design a fair test, and we'll probably do this largely in class together. Okay, so dropping things near the earth has to do with free fall. What we're going to look at now is the case where we ignore air friction. The word here that you can't quite read is free, and this one is near. So near the earth, the gravitational field can be considered to be uniform. If a body is dropped in this gravitational field, its motion is called free fall. The acceleration of free fall for a body near the earth is a constant and equal to 9.8 meters per second squared. Now what it says behind this graph here is this ignores the effect of air resistance, which provides a force opposing the motion. So if there was no air resistance, the acceleration of any body dropped would be a nice constant line like this. Now, of course, in real life we do have air resistance to worry about, as the paper cup experiment demonstrates. So that's the next thing we'll look at. Okay, so as the velocity, the word there is as the velocity of a falling body increases, the air resistance force also increases. Hence the acceleration of the falling body decreases. The acceleration will continue to decrease until it reaches 0, at which point we say that the body has reached its terminal velocity. An example would be a parachutist doing a jump. So here is the graph of a parachutist jump. You can see the first section just down here, very steep slope. The speed is increasing rapidly, tailing off as air resistance increases due to the high speed, reaching a constant velocity called terminal velocity. When the parachute opens, a sudden deceleration, a very rapidly decreasing speed, shown by the negative steep slope of the graph. And that, of course, once that balances with gravity again, force of gravity, you have another terminal velocity, a small one here, so that it's safe to finally impact the ground as the final deceleration, just as the parachutist lands.